Now let's take a look at some simple rough turn, bore, and face routines. Sometimes you only need to take a simple rough turning cut or a rough boring cut. The G90 command is a handy cycle for just this purpose. The G90 cycle is very simple to program. Like the G71, G72, and G73 cycles, the tool must be positioned at a convenient start position. This position must be slightly away from the face of the part and slightly larger than the stock diameter. For a boring application, the tool must be positioned slightly smaller than the existing hole. The G90 cycle makes 4 moves. It will rapid down to the X position, feed to the Z position, feed back to the starting diameter, and finally rapid to the starting Z position. The cycle consists of the G90 command. X defines the cutting diameter, Z defines the position to turn to, and the feed rate is specified with the F word. Look at this program and you'll see that the first line, the GOO X 2.425Z.05, positions the tool at what we're calling the convenient starting position. Notice that it is 50 thousandths away from the face of the part, and also notice that it is 50 thousandths larger in diameter than our rough stock. The second line is our can cycle, G90. It gives it a diameter to cut to, in this case 2.125, and a position to feed to along the Z-axis, in this case minus 1.245 inches. This is a roughing cut, so we do want to leave material at the end of that turn. And finally, our feed rate is specified at 12 thousandths per revolution feed rate for this roughing application. The cycle is modal and will repeat by simply specifying a new X diameter or Z position on a line by itself. To stop the cycle, command a GOO or other type of motion. Notice that in our program, line numbers 240, 250, 260, and 270 all contain X values. Each of those is a diameter that we want the rough turning cycle to machine at. We would never include a GOO on any of those 4 lines, as if we did, what would happen was the GOO command would then cancel the G90 cycle. So as you can see by the simple format here, we command our G90 cycle by instating it with the G90 command, and then every diameter that we want to cut after that, we just simply list a new X position or a new diameter. If the length along that cut were to change as well, we could also include a new Z value at each one of those new diameters. Notice that line number 280 is going to send our tool to the tool change position, and it would be part of our tool ending format information. It is that line there that will cancel the can cycle of G90. The G90 command works equally well with a rough boring operation. The convenient start position would be slightly smaller than the existing hole, and the Z position would be slightly away from the face of the part. If you remember our convenient starting position for our G71 rough boring operation, the basic rules apply here as well. For the boring operation, start at the small diameter and program larger X coordinates for each pass. As you can see on line number 520 in our program, we select a convenient start position of 700 thousandths of an inch, which is 50 thousandths smaller than our existing hole. Line number 530 instates our can cycle with the G90 command, and our first cutting diameter will be at 950 thousandths of an inch, and we are going to be boring to a depth of 1 inch 245 thousandths at a feed rate of 12 thousandths per revolution. Our second cut, which is commanded on line number 540 will be at a diameter of 1.15 inches. Line number 550 cuts our third and final diameter at a diameter of 1.295 inches. Finally, line number 560 will rapid the tool back to our tool change position, and of course the GOO command will cancel the can cycle specified with G90. A taper can be machined with the G90 cycle as well. You would include an R word that specifies the amount of taper per side on the part. The value specified by the R word will shift the starting diameter of the cut. When the tool reaches the end move of number 2, shown in the diagram below, it will be at the X value that was programmed with the X word on the G90 line of the program. So if we look at our program example here, we have our command G90 X 1.25, and that would be at the position where lines 2 and 3 come together. Our Z position of minus 1.25 inches, which would be down where position number 3 is in our diagram. The R minus 0.375 will shift the starting diameter, which is on the right edge of this near position number 1. It will shift that 375 thousandths per side smaller than the 1.25 dimensions specified with X. And finally, our feed rate at 12 thousandths per revolution. Now the thing that you must understand, if we specify an R positive value, we will shift the starting diameter larger than what is specified with the X word. If we program an R negative value, we will shift the starting diameter smaller than the position specified with the X word. It's just a matter of understanding that we're shifting the start point, not the end point of that taper. A related cycle is the G94 rough face command. This cycle works just like the G90 command, except that it will face the part. In other words, it is going to be cutting along the X-axis instead of the Z-axis. The convenient starting diameter would be slightly larger than the stock diameter and slightly away from the face of the part, just as we did with the G90 command. This program demonstrates the facing operation. We call up our tool with offset 2 on line number 200. Line number 210 gets our spindle running. Line number 220 gets the tool at our convenient starting position. Line number 230 initializes the G94 rough facing cycle, and we're going to be facing down to a diameter of 705 thousandths, which is slightly larger than the print is showing, as this is a roughing operation. And our first cut will be at a Z position of minus 125 thousandths. We will perform this facing cut at 12 thousandths per revolution feed rate. Line numbers 240, 250, and 260 progressively step the tool towards the left, taking consecutive facing passes, each one being approximately 1/8 of an inch. Line number 270 will rapid the tool back to the tool change position, canceling our G94 can cycle. A taper can be machined on the face by including an R word. The R word specifies how far and in which direction to shift the starting Z position. The programmed Z position would be the point where moves 2 and 3 come together. In our example here, we have the command G94 X 0.705, which is down at that position number 3, Z minus 0.125, which would be at that point where 2 and 3 come together on our diagram, an R minus 0.1875, which means that it's going to shift the start point of that movement to the left or closer towards the chuck 187.5 thousandths, and that facing cut will be at 12 thousandths per revolution. Just as we had to do with the turning operation with G90, the R word being negative or positive is going to either shift the start point closer toward the chuck or further away from the chuck. An R negative value would shift the start of the cut closer to the chuck, as we have demonstrated here. An R positive value would shift the start of the cut away from the chuck. Now let's take a look at threading with the G76 cycle. This will be our example part for this lesson. What we need to do is machine a 1.5 inch 6 UNC thread on this workpiece. We won't bore you with the details of roughing the part out, as that is a relatively straightforward process with the G71 cycle. We're strictly going to focus on the threading operation. The G76 cycle will perform most of the work for us. Here you can see the threading tool coming along and cutting the thread on the workpiece. You'll notice that the V shape of the tool is going to create the V shape of the thread. Threading is a simultaneous roughing and finishing operation. In almost all situations, the roughing and finishing are performed with the same tool. There are rare instances when you need to rough with one tool and finish with another, and that can be accomplished as well. Here you can see that the G76 line is formatted like that of the G71, G72, G73, 4, and 5 cycles. It requires 2 lines of program information. We'll take it word by word as we go through this, because we also need to learn about some of the terminology used with threading. For now, what I want you to understand is that a threading operation is a little bit different than any other type of operation performed on a turning center. And the biggest difference has to do with when the tool is cutting on the workpiece. If you think of the thread as a long spiral or a spring shape to it, that spiral has one definite start point at the front of the workpiece. The machine has to have some synchronization between the rotational position of the part and when that tool starts moving into the front of it. Because as mentioned before, we need to take roughing passes and we need to take a finishing pass. That could be performed with the same tool or with separate tools. But the machine has to go into a synchronization mode to synchronize the rotational position of the spindle and the Z position of that tool. And that's what the G76 cycle will do for us. In another lesson, we'll learn that the G92 cycle and G32 also perform this synchronization for us. The major diameter is the larger diameter of a thread, whereas the minor diameter is the smallest diameter of a thread. Now that would apply to both male and female threads. On a female thread, the major diameter would still be the larger diameter, and the minor diameter would be the smaller diameter. However, when you think about the turning operation that must occur before the threading operation, for OD threads, we are going to turn the major diameter. For ID threads, we would bore the minor diameter. That is the big difference. In our threading cycle, our G76 cycle, we would program the threading tool to cut at the minor diameter for an OD thread. And when we're using the G76 cycle for an ID thread, we would program the G76 cycle to cut to the major diameter. The blueprint itself will give us much of the information we need to program that G76 cycle. The print will give us the major diameter, it will give us the pitch, and it will give us the thread length. In our example part here, our major diameter will be 1.5 inches, which is noted by the 1.5 inch -6 UNC thread. That 1.5 inch is telling us the major diameter. The pitch of the thread is the -6 part of the thread designation. That 6 means there are 6 threads per inch. In the United States, we always specify a thread pitch on a blueprint as telling us how many threads per inch the thread has. The thread length is shown on the blueprint as a 1.375 dimension. On this blueprint, we've also given to you the minor diameter of the thread. Rarely is the minor diameter given on the print. Therefore, you must look for the minor diameter in some form of a reference book. There are many good publications and great reference texts relative to manufacturing threads. If you do not have one, I highly recommend that you purchase one because it will become a very, very close ally in the future when you are writing programs. Another area of concern with threading has to do with what part of the tool we are actually positioning. Some companies will position the left edge of the tool, whereas other companies, when they're programming it, will position the point of the tool. It is my opinion that positioning the point of the tool is the most critical and the proper way to do it. However, that puts upon to the programmer as well as the setup person the responsibility of making sure that the left edge of that tool will not ram into the face or a shoulder on the workpiece. Again, what we're talking about is that programmed point, and that is the point of the insert that we are going to be positioning when we are positioning that tool. You, as the setup person or the programmer, has to watch for that width of the insert to make sure that the left edge of it does not bump into a face on the workpiece. As mentioned earlier, the pitch is always specified as the number of threads per inch here in the United States. So when we see a specification 1 1/2 inch dash 6, the 6 means 6 threads per inch. Now what we're going to do is convert that to what's called pitch in inches. What we want to know is the distance from one peak to the next as shown in the diagram below. This is very easy. All we need to do is take 1 divided by the number of threads per inch. And in our example, that will be 0.1666. Now the other thing that you must understand for threading is that the pitch will always equal the feed rate, and vice versa. If you change the feed rate, you would change the pitch. So therefore, as a setup person, you would never be able to change the feed rate for a threading cycle. If you change the feed rate, you would change the pitch. And obviously, if you change the pitch, this part would not fit with its mating component. If you remember back on our lesson for the convenient starting position for our multiple repetitive cycles G71 through G75, we had to have the tool positioned at a certain point where it could safely perform its machining operation for that particular cycle. Well, threading is no different with the G76 cycle. We still have a convenient starting position. However, it's a little bit more technical. For the z-axis, we want to provide enough distance for the tool to accelerate up to speed. Remember, the tool is going to go from dead stop to a relatively fast feed rate when threading. And because it has to accelerate very, very quickly, we have to give it a little bit of distance so that it can do it. Otherwise, our first few threads will not have a perfect pitch. What we have found is a general starting point for calculating that acceleration distance is to take 2.5 times the pitch. That 2.5 is just a numeric constant that we've found in our applications to work fairly well with most equipment. Depending on your equipment, you may have to go a little bit larger on that number to give it more distance to accelerate. On some of the newer high-speed machines that can accelerate very rapidly, you may be able to even reduce this amount. But in our example, we're going to say it's 2.5 times the pitch. And in our case, our pitch is 0.166. So if we take 2.5 times 0.166, we end up with 0.4165 as our z-axis starting position. And this would be for our convenient starting position of the G76 cycle. It would also apply as a convenient starting position for any other type of threading operation. The convenient starting position for the x-axis of this tool needs to be at a point slightly larger than our major diameter. When we are machining an ID thread, we would want the tool to be at a position slightly smaller than the minor diameter. Now I know we've covered a lot of new terminology so far, as well as a few parts of the CAN cycle. Now let's take a look at some of that terminology and see how it fits into our G76 cycle. Our first line before the G76 cycle positions the tool at our convenient starting position. Our major diameter happened to be 1.5 inches, so we went slightly larger than that at x of 1.6. We calculated our Z convenient starting position by taking 2.5 times our pitch, which in this case was 0.1666, and we came up with a value of 0.4165. So that became our convenient starting position for the Z-axis. The first line of the G76 cycle, we really haven't figured anything out for that yet. However, the second line of the G76 cycle, we found that the X word on that line is going to be programmed with our minor diameter, which was given to us on this particular blueprint. The Z word is the thread length. We would also get that from the blueprint, and in our case it happened to be 1.375. And earlier we told you that the feed rate had to equal the pitch. There was no way that you could change the feed rate without altering the pitch. So in our case, we took 1 divided by 6, which was the number of threads per inch, and that gave us 0.1666. Hopefully so far you kind of understand where some of this information is going to go in your program. We're going to take a look at the remaining words in the next few slides. The first P word in the G76 cycle will actually have 3 different items defined by it. The P word cannot have a decimal point, and in this case it must be 6 digits long. The first 2 digits, as we have shown here, P01, would specify the number of finishing cuts. The finishing cuts are sometimes called spark out passes, free passes, or some people may even call them spring passes. If you specify a value of 01, you will get 1 extra finish pass at the final diameter. If you specified a value of, say, 05, you would get 5 extra passes at that final diameter. The purpose of this is to take the spring out of the workpiece. If you have a very long, small diameter workpiece, there will be a lot of spring in it. It will want to bend away from the tool as it is being cut. And the purpose of these spring passes is to take away some of that deflection by cutting with the tool at the same diameter several times. We have found that for most general applications, taking 1 spring pass will suffice. The second 2 digits specify the retract distance at the end of the thread. This is also called a thread chamfer distance. If we look at the diagram below, we have the tool there above the workpiece, and we have a red line drawn to represent how the tool path will look. At the end of that tool path, you'll see that there's a slight angle coming up on that red line. And that is the area that we're talking about. That slight angular move going up and towards the workpiece is that thread chamfer. Now, if we were to specify a value of 10, as in our little example right by the workpiece, we're saying that we want the tool to start retracting out of the thread 1 pitch from the end. If we were to have specified a value of 00 for those second 2 digits of the P word, the tool would retract straight out on x-axis when it got to that endpoint along the thread. This is handy when we're threading up against the shoulder, as in this example. However, when you are threading on a straight shaft, where there is no fear of the tool hitting the shoulder on a workpiece, allow the tool to retract with a chamfer. It makes a better looking part, and it is less damaging to the machine to have the tool retract at that angle as shown in the diagram here. So basically you have two settings that you would generally use. A value of 0, 0 for these second two digits, which would force the tool to retract very quickly and sharply out along the x-axis. Or a value of 1, 0, which would mean that the tool will start retracting one pitch from the end of the thread. The third two digits specify the thread angle. For many threads, this is a 60-degree angle, but always check a reference manual and the blueprint for the specific thread you are programming. This is used to control the infeed angle of the cutting passes, and we'll take a look at that in a little more detail on the next slide. The third two digits of the P word control the infeed angle. We have specified a 60-degree infeed angle because we are cutting a 60-degree V thread. When we specify a nose angle for the threading insert, the tool will cut only on the front edge as we have shown in the diagram below at the left. If we specify a nose angle of 0 degrees, the tool will have an infeed straight into the thread, as shown in the diagram below and to the right. Now the difference in cutting conditions is quite severe for these two types of thread. If you think about the chip that would be formed during this cut, while the tool is feeding straight in on the x-axis, the chip would be V-shaped and it would be very difficult to control. This would cause the chip to bind up in our thread. In the other example at the left, where we specify a 60-degree nose angle, the chip would be formed on one side of the insert, and it would flow freely out of that thread. This has a lot to do with the surface finish of the thread after it is completed with the machining operation. Generally speaking, it is most ideal to always specify the proper nose angle for your insert and thread. For acme threads that are square in shape, you would specify a 0 to 0 for your tool nose angle. Let's take a moment to quickly review this P word again. The first two digits will specify the number of spring passes. These will be extra passes at the final cutting diameter. The second two digits will specify the retract distance at the end of the thread. A value of 0, 0 would be no distance. The tool would retract very quickly along the x-axis. A 0.5 value would mean 1/2 a pitch. 1/2 a pitch from the end of the thread, the tool will start to retract on the x-axis. And a value of 1, 0 would mean that the tool will start to retract along x-axis 1 pitch from the end of the thread. The third two digits specify the thread angle. A value of 0, 0 would mean no angle, and the tool would cut with the front and the back, as in the case of an acme thread. A value of 60 would specify that the tool would only cut with the front edge. Now you will have to check your manual for the specific settings that are allowed as far as tool nose angle. There are standards that are followed in the manual for your machine relative to the standards used in industry for threads. A little bit later in this lesson, we're going to learn about the infeed amount per each roughing pass. However, the computer or your CNC control is what's going to calculate the amount of infeed for each roughing pass. But at some point, it's going to calculate a value that is extremely small. And what we want to do is limit how small that amount can be. The Q word on the first line of G76 controls this for us. The Q word does not allow a decimal point, so we would have to program it as if it were 4 decimal places of precision. In other words, a Q value of Q0010 would be equal to 1/1000th of an inch. Q0100 would be equal to 10/1000ths of an inch, and so on. But all we're really doing is specifying a minimum infeed amount. A value that we found that can get you started or pretty close would be 2.5/1000ths. Obviously, for softer materials such as aluminum, brass, and other non-ferrous materials, you can have a larger minimum infeed amount. But for some of your tougher alloys, such as Inconel and Hastelloy and some of the other stainless steels, as well as tool steels, you may need to actually have even a smaller amount for your Q value, which is specifying the minimum infeed amount. There's yet one more variable on this first line of G76, and that's the R word. Now, the R word can use a decimal point, so that's kind of a nice relief. And all the R word is specifying is our last pass cut amount. Our minimum infeed amount was controlled by the Q word. The R word is just simply saying that our very last cut, we're going to take the amount that we specify here. Now on to the second line of G76. We've already learned that the X word will be our minor diameter for a male thread, and the X word would be the major diameter for a female thread. The Z word specifies the length of the thread, or the Z endpoint of that thread. The P word, again not allowing a decimal point, specifies the radial thread height, how far it is from the peak to the valley on one side of the thread. This is very easy to calculate once we know the major and minor diameters. We would simply take the major diameter minus the minor diameter and divide it by 2, which in our case would be 0.0995. And because we can't use a decimal point, we would program that simply as P0995. And now finally we get to specify the first pass depth of cut. And that is done with the Q word on the second line of G76. Here we have a value Q0150. Notice no decimal point, and what we're specifying in this particular case would be 15/1000ths of an inch. To figure out what your first pass depth of cut is, you really should look in the tooling catalog of the manufacturer that makes the tools that you are using. There are many other references relative to the threading operation specifying the number of passes and the first pass depth of cut. Obviously, with harder materials, you would most probably take a smaller first pass depth of cut. And for softer materials, non-ferrous materials such as brass and aluminum, or even the plastics and phenolics, you would take a larger first pass depth of cut. What the control will do then, from that point, it will infeed an ever decreasing amount. So the first pass might be 15/1000ths of an inch infeed. The second pass might be 14/1000ths. The next pass after that might be 12/1000ths, then 9, then 8, 7.5, 7, 6.5, 6, and so forth, working its way down to a smaller and smaller infeed amount with each successive pass. And if you remember, back up on the first line of G76, the Q word there will specify the minimum amount allowed for the infeed cutting depth. So again, to repeat, the second line of G76, the Q word specifies our first pass depth of cut. You want that as large as you safely can do and yet still maintain good tool life. But then after that pass, each successive pass will be infeeding a shorter distance or a smaller distance. Now let's take a look at the whole program section for this particular tool. As always, we describe the tool in our comments with the parentheses. We call up tool 8 with offset 8 on line number 800. Line number 810 sets the machine into direct RPM mode. Threading operations must always be performed in direct RPM mode, which means we would have to convert from the recommended surface feet per minute into an RPM. And in this case, it came out to 675 RPM. And we're turning the spindle on in forward rotation with the MO3 command. Line number 820 rapids the tool into position for our convenient starting position. The X value, 1.6, is 100 thousandths larger in diameter than our major diameter of this thread. The Z, 0.4165, was calculated by taking 2.5 times the pitch for our acceleration distance. That's how far we want to be away from the front of the part. And finally, the coolant is turned on with the MO8 command. Line number 830 is our first line of G76. And the P word contains 3 different bits of information. The first 2 digits, 01, specify the number of free passes. Once the threading tool gets all the way through with all of its roughing and finishing passes, it's going to take 1 extra finishing pass. The next 2 digits, 00, specify a retract distance of 0. In other words, when the tool gets to the end of the thread at that Z minus 1.375 value, it will then immediately pop out on the x-axis. The next 2 digits, 60, specify the tool nose angle, which would also be equal to the thread angle. And in this case, it's 60 degrees. And our infeed would be at an angle so that the cutting would always occur on the front edge of that insert. The Q word, again not having a decimal point, is specifying 2.5 thousandths minimum infeed amount. The R word there is specifying that the very last cutting pass will be at a depth of cut of 1/1000 and 2/10 of an inch. Line number 840 is our second line of G76. The X word is specifying the minor diameter, as this is a male thread. If it were a female thread, that X value would be the major diameter. Our Z value is the end point of the thread, and the P word is specifying the radial height of the thread, the distance from the peak to the valley per side on the thread, which in our case was 0.0995, and we calculated that by taking the major diameter minus the minor diameter and dividing that amount by 2. The Q word, 0150, is specifying our first pass depth of cut. And in this case, that's 15 thousandths of an inch. And finally, the feed rate at 0.1666, which is our pitch. And we converted our pitch from the number of threads per inch into the pitch in inches by taking 1 divided by the number of threads per inch. Line number 850 simply rapids the tool to our safe tool change position, and line number 860 is our optional stop command. As you can see, this program really isn't that long or complex for the threading operation. However, I will admit there is an awful lot of control and an awful lot of details with that G76 cycle. So hopefully you've taken really good notes, because you're going to be doing an awful lot of threading in the future. We can also cut a tapered thread, as in the case of a pipe thread, with the G76 cycle. To specify a taper, we add an R word to the second line of the G76 cycle. What that will do is shift the starting point on x-axis by the value specified in the R word. Now if we look at the diagram, we can see our minor diameter is still specified near the end of the thread. The R value is specifying the amount of taper per side, and if we specify a negative value, that means the tool will be shifted closer towards the center line, which gives us the proper direction of taper for a pipe thread. Obviously, you would have to calculate out that R word depending on your thread length and the actual angle. But what you have to be careful with on that R word is when you are trigging it out or calculating it, you have to calculate it from where the tool is starting at for your convenient starting position on Z-axis all the way back to the end of the thread at our Z word on the second line of G76. But that's how we get a tapered pipe thread. We simply add an R word to the second line of G76. And for male threads, it would be an R negative value to get the proper direction of taper. The G76 cycle works equally well for ID threading. When we are machining a female thread, we would also call this ID threading. The differences would be that the X value on the second line of G76 would be now called the major diameter. The convenient starting diameter would be slightly smaller than the minor diameter, which is opposite of a male thread. Also, taper threads can be cut with an R, but this time we use a positive value instead of a negative value because we want the start point of the thread to be shifted larger in diameter. But the G76 cycle, as you can see in this example, works equally well for male threads as well as female threads. Let's review the G76 cycle one last time. The first line of G76 has a P word that is going to specify three things. The first two digits specify the number of spring passes. The second two digits specify the retract distance at the end of the thread. The third two digits specify the tool angle, which will control the infeed angle of the tool, forcing it to cut only on the front edge of the insert. The Q word is specifying our minimum infeed amount. The R word is going to specify the very last pass infeed amount. It should be noted that the spring passes will occur after that last pass infeed amount. The second line of G76, the X word equals the minor diameter for OD threads and the major diameter for ID threads. The Z word is the thread endpoint. The P word is going to specify the radial thread height. We calculated that by taking the major diameter minus the minor diameter and dividing by 2. Notice there is no decimal point for the P word. The Q word specifies our first pass depth of cut, and we would get that from our tooling catalogs or information from the tooling manufacturer. They would be the ones to recommend to you how much your first pass depth of cut should be for the workpiece material you are cutting. Also note, the Q word does not allow a decimal point, as with any other place in our program. The F word would be equal to the pitch of the thread in inches. The specification on a blueprint is going to give you the pitch as specified by the number of threads per inch. To convert that to the pitch in inches, we take 1, as in 1 inch, divided by the number of threads per inch. R would be our taper amount per side for a tapered thread. To get the thread to be smaller at the front of the part, we would use a negative R word. To get the thread larger at the front of the part, we would use a positive value for the R word. For the 6T family of controls, the G76 cycle is slightly different. We start out, it only has one line as opposed to two lines. The X word would specify the minor diameter for OD threads and the major diameter for ID threads. The Z word would specify the thread endpoint along the Z axis. Those are basically the same for the 0T and 3T family of controls. The K word is going to specify our radial thread height. We get that by taking the major diameter minus the minor diameter and dividing by 2. The D word will specify our first pass depth of cut. Notice also no decimal point for this word either. The A word is going to specify the angle of the thread. The F word will specify the pitch of the thread in inches. And we get that by taking 1 divided by the number of threads per inch. And finally, I will specify the taper amount per side. A negative value would make the front edge of the thread smaller in diameter. An I positive value would make the front edge of the thread larger in diameter, as would be the case for a female pipe thread. You'll also notice that in the 6T style of programming, there is a lot less control over the cutting conditions. You should check with the programming manual, the FANUC manual that came with your machine, and see about the parameters that also help to control some of the cutting conditions, as the cutting conditions are controlled more by parameters with the 6T programming style. And just as a reminder, the feed rate must equal the pitch. You cannot change the feed rate of a threading cycle. Whatever the pitch is what is going to dictate to you what the feed rate will be. Also, the spindle must be programmed in RPM mode, G97. What we have to do when threading is we have to maintain a very consistent and a very constant spindle speed. If you remember, G96 would vary the RPM depending on what diameter the tool is currently positioned at. And if we were to allow that to happen during threading, our pitch would be varied terribly, and we would have a horribly imprecise thread. So to ensure a nice accurate thread, we must be in RPM mode when performing a threading operation.